Welcome to the video lecture about K-means properties. This presentation is based on this article. Okay, so K-means is well-known algorithm that for a given set of input points, it aims at finding the clusters, so it partitions each of the data points to its own cluster, finding the partitions, and also a set of centroids representing of each cluster. So that is the output of K-means, and how it selects it, it tries to minimize this objective function called sum of squared errors, which is for every input point, it calculates its nearest center point, nearest centroid or centroid of the cluster that it belongs to, squared error, and then sums it up, and that it aims at finding the minimum. Now, we don't, in this presentation, we don't question about the suitability of this SSE cost function. We just assume that it is sensible for the data. And second, we assume that K is known. So K-means algorithm is a two-step process. So for a given input solution, so first you may notice that we need to have some initial solution. And this is typically the selection of, we select K random data points and set them as the centroids to start with. And the output is improved set of centroids and the final partition, the nearest centroid for each data point, so partition and centroids. So at first step, what it does is to, it's in this assignment step, it finds for every input data point, finds its nearest centroid and make the cluster assignment. So this partition label will indicate which cluster it belongs to. And after this has been done, then at the second step, centroid step, we recalculate the new centroids for every cluster. So if these points have been clustered together in the same cluster, no matter where the original centroid was, so let's suppose the centroid was here, and all of this were nearest to that. So now with the centroid step calculates the average, the mean vector of all of these in this cluster, and sets the new centroid in this average location. And then it repeats these two steps. And both of the steps either keeps the solution same or makes some improvement. So in practice what will happen is that the centroids keeps on moving and the borders will be fine-tuning. For example, here we have before the iteration this solution, and after applying one round of K-means iteration, you can see that this centroid here has been moved a little bit closer to these points. So when new points join to the cluster, they will attract the centroid and make such movement. Also in this case the centroid is here, but because here more points are joining to this cluster, they will attract the centroid, it will move a little bit to the up direction. And this kind of movement typically happens just few iterations or up to something 25, 35, or in some cases even up to 100. But anyway, some reasonable number of iterations will be applied, and when no changes happens anymore, then K-means will stop. So now I want to find out how well K-means performs in this optimization task. So given the sum of squared error, how good quality, how good result it gets, but not only the objective function value itself, but does it really find the correct clustering? Okay, here are some examples what kind of errors happens in K-means. So this is the final result of one K-means run, started for some random solution, and these are the centroids that it managed, and these are the clusters that it managed to find out. Okay, so we will see that there are problems. So here are one centroid, and here's another one. That should be located somewhere else. Here we have one cluster, but there are two real group, and same here. So this kind of allocation errors where the centroids are wrongly located, this typically happens. Also, if we use some naive initialization technique, Another alternative is to use random partitions. So this is example what will happen with random partitions and what will happen with k-means after that. So this data set has quite many clusters and they are forming this kind of a Sini curve in the data space. They are close to each other, but yeah. Okay. These centroids here, can't see very clearly what they are there because they are so overlapping each other. So the idea of this initial technique was this is so-called random partitions, where each data point is put into random cluster, and then the resulting clusters, the average of these clusters are taken, and the centroids will be the initial solutions. So what will happen that if we take one data point somewhere here, another one here, another one here, here, just random data points becoming to the same cluster, the center point will be somewhere in the central area of the data space. And same will happen with all clusters, so we will get this kind of initialization. Now, okay, so it shouldn't matter so much on k-means, but what you can see, after we start to apply k-means here, the final result is that certain centroids have been managed to move, and they are conquered some kind of clusters here. But because this structure has limited dimensions, kind of, that it's basically one-dimensional curve what all the data points are following, so it doesn't allow enough centroids to move there, and we will have lots of centroids remaining here. So it depends also how good is the initial solution. So this is another problem of k-means. Okay, so I have 4 questions I want to give answers in this presentation. So how much the properties of the data affect how well the k-means perform. So I will study 4 different properties. First is the overlap. So it means that the clusters and the data points, they are not well separated, that you just need to find the clusters here and there, but they are overlapping. So how much this kind of overlap affects how well the k-means perform. Second is the number of clusters. Okay, here we have 3 clusters, but what about if I have 4, 5, 50, 100? How does it affect how well k-means perform? Third is the dimensions. So now in most of my examples the data has only 2 dimensions. They are the x-axis and then there's the y-axis. So this is just because this is the only possible simple visualization I can make. But in practice the data may have, here is 1 dimension, 2 dimensions, 3 dimensions, but it depends how many attributes the data really have. So it can have 10, 20, even 100 or 1000. And this is called because now the space that the data points lie in, so this is called dimensions or dimensionality, and it's just how many attributes. So what will happen with k-means when we increase the dimensions? Okay, question number 4 is unbalance of cluster sizes. So what if the clusters are not of the same sizes, but we have one really big one and a couple of small ones, or just whatever different sizes? Okay, to study these properties, we create so-called clustering basic benchmark data set. In this set, there are 6 different data or set of data sets. All of them are existing already before, but not so well documented. So I try to summarize here what are the data sets and what are the special properties. So first, A data sets. So A data sets has a varying number of clusters. There are 3 different sets, A1, A2, A3, clusters 20, 35, and 50, 150 per each cluster. S datasets here, overlap is changing. Third set, dimensional sets, the dimensions are from 32 to 1000. G2, we have only 2 clusters, but the dimensions and the overlap has 2 parameters. So this is actually a big collection of I think 100 different data sets with these 2 parameters, overlap and dimensions are varying. And Birch has this funny structure, so they will reveal something, and then we have one unbalanced data sets. So this I will define as a basic benchmark data sets, and the reason why I have selected these data sets is that they are kind of easy enough that a good clustering algorithm is able to solve them, but also they are challenging enough so that the bad algorithm will easily fail with some of them or even most of them. And the second reason is that the varying of these different parameters of the datasets, we can reveal different dependencies. For example, this A dataset, so the number of clusters really, because if you look carefully, these datasets are actually subsets of each other. So the size of the clusters, the distance from each other, it's approximately constant, and only the number of clusters is increasing when we move from A1 to A3. Then in S sets, we have the same number of clusters, and okay, here the main aspect that is varying is that in the S1 dataset here, you can see the clusters are quite well separated. We have this kind of measure overlap. So this is the smallest overlap of the clusters, and S2 a little bit more overlap, S3 quite a strong overlap already, and the S4 is really serious overlap. Okay, according to this measure, it doesn't look that serious, but if you look at the picture, you can see that yes, it is a little bit messy, but we can still recognize where the clusters are, and any good algorithm will have no serious problems to solve it. But if the algorithm is too simple, yeah, it's a good test that does the algorithm work on this or not. So by default, you would assume that this is the most difficult from these, right? Then unbalanced datasets, 8 clusters, they are also quite well separated. Okay, they are a little bit overlap, like here you can see some points are mixing with the other clusters and this area. Here they are well separated but not so far from each other. But the most important thing is here that they are different, completely different sizes. They are very dense datasets here, very dense clusters here, whereas they are quite sparse. Also, the standard deviation of this distribution is 3 times more than those on the left. And these 2 areas are also far from each other. So there should be no problems for mixing them. So then the dim sets, these are also quite well separated. Actually, they are really well separated. Now, this is the smallest dimension is 32 and then the highest 1000. And because I can only show 2 dimensions in this slide, it may look that the clusters might be overlapping, but they are not. So in the 32-dimensional space, they really are well separated. So this is just to test the dimensions, no other conflicts, or no other challenges should appear there. And then these G2 datasets, so these are really simple. 2 centroids at these locations, 500, 600, and they are 2 varying parameters, so the datasets have been named accordingly, so that this one is the dimensions and this one is the standard deviation, how far the points are from the cluster center. So they are generated data, so that in this case they are 2 dimensions here, and with 30, standard deviation is 30 units, so you can see they are a little bit overlapping. When the standard deviation increases to 50, they are already much more overlapping. 70, they are really overlapping, and the final is 100. They are almost mixing completely, merging together. So this should have very good capability to find out how this overlap happens. Okay, and then we have the merged datasets. They originally have 3 different datasets. In this, I will use only the first 2 because the third one doesn't fit for the sum of squared error criterion. But these 2 are very good test cases. Merge 1 has a 10 times 10 grid, and the merge 2 has a Gini curve. So these are the parameters how the Gini curve has been generated. So you can see the clusters are reasonably well separated, at least in the merge 2. Merge 1, it looks like a little bit more overlap, and here they form a 2-dimensional grid, and here just 1-dimensional Gini curve. So, and the second aspect of this is this has a little bit more data points than the others. So all of these data sets, they are not meant to be any large scale. So this is a little bit testing the number of data points also, but more important, it actually have quite many clusters, 100. So this is also stress test kind of. And also the merge 2 have been used in the following way. So we have reduced the number of data points first by random subsampling. Here in the left, we have created a sequence V2 random by randomly removing 1000 points from here to here. Then 1000 more points have been removed, and so on, until we reach to 1000 points. So this will create a series of varying number of data points. The second subset, V2 sub, has been also removed 1000 data points one by one, but in this case I have been removed one cluster at a time. Here one more cluster has been removed, here one more, and so on, until here we have 3 clusters, 2 clusters, and 1 cluster. So you can see that the rest of the data is actually the same for the others. It's exactly the same structure, same overlap, deviation, all other parameters are the same, except the number of clusters is reducing. So, okay, so a little bit more about the properties of this data to get better understanding what they are. So I use these 5 different measures: overlap, contrast, intrinsic dimensionality, edge index, and distance profiles. Okay, since the overlap is one important characteristics for k-means, or how k-means perform, so let me think about 2 different ways to define it. Okay, first one is that if we have the ground truth classification, so ground truth partition, like in these G2 data sets, we were wise enough to actually store the partition labels, because they were generated so that we have a center point here, and then we added according to Gaussian distribution points around it using certain parameters, and then we know that this point were originated from this centroid, whereas these points here and also these points originated from this centroid. Now we can calculate so-called misclassification probability for taking any data point, and as we know that it's coming from this cluster, we also calculate what is the nearest centroid. And in this case you can see the partition border is somewhere here. So it's nearer to the wrong cluster. And all of these wrongly classified points are marked here with this kind of a bigger color. So now calculating this kind of misclassified points, we will get that in this case 20 points are incorrectly or misclassified. So 20 out of 2048, it means that about 1% of the points are misclassified. So the overlap on this, according to this misclassification, is given. Okay. However, we don't have for the other data sets, we haven't the ground truth labels that which cluster the points were generated. We just have the points, so all we have, we know what is the nearest. So we cannot use this same unless we have the ground truth labels. So in this kind of data sets, we use alternative estimation of the overlap. So what we do is to calculate the distance to the nearest centroid and to the distance to the second nearest centroid for every data point. So let's suppose this point is at the border here, So its nearest centroid is, okay, if it's at the border, it's either way, but the second nearest is at the equal distance. So we calculate these two distances and then the ratio, squared ratio, give the estimation, we call it so-called confusion. So the higher the ratio, higher the confusion between these two clusters. And then we take any data point. If we take here, it is 1/4 to here and 3/4 to the there. For their ratio squared, we get confusion rate 0.11. And this we can do actually any point. Now you can think about this point here. It might look that, yes, it's clearly belong to this cluster because this is in the wrong direction or something. But then again, the algorithm doesn't know it. For the algorithm, we just have two distances here, and it must be decided that which cluster it belongs to. So the distance to here is 0.25 and here is 0.75. So again, the confusion ratio is this 0.11 for that point. So then we sum it up, all of this, and that take the average confusion as the overlap estimation for this this data set. Okay, then the contrast. This is another estimation of how diverse are the data, and this is taken so that for we calculate for any data point its distance to the nearest another data point and furthest data point, take the difference. So how far is the nearest, how far is the furthest, and this difference gives estimation of the distances. And then if we divide it by the minimum, we get the relative difference. And then if we take again average, or in this case we take the median of all of these numbers in the data set, we can get some estimation of how much variation is the distances have with this data set. So two examples here. With the dim data set, when the dimensions increase from 32 to 1000, we can see that yes, the contrast it is increasing. This is logarithmic scale, so the increase is real, but not that strong. So the higher the dimensions, the bigger the difference between the distances come, which is kind of understandable. Okay, G2 data sets, however, it goes actually the opposite, and this reveals that these two data sets have something remarkably different. So when the dimensions increase here, the contrast actually goes down. Okay, we will come later to see where this originates from and why this happened, but this data sets have different properties. Okay, the other measure we have intrinsic dimensionality. This is okay. Now we know the real dimensions. Most of them are 2 dimensions. The G sets has varying dimension. Dim sets also varying dimensions. But if you compare verge 1 and verge 2, well, because intuitively you can think that this is a 2-dimensional data set, and this is it could be considered as a 1-dimensional because the data are in linear. You have kind of order. The clusters at least are ordered in a point. But then again, they have kind of complex structure, which is not trivial for algorithms to find out. So yes, so this intrinsic dimensionality, it calculates the average, squared average of distances and divided by the variance of these distances. And this gives estimation of this complexity. And these numbers give some estimation. For example, with the unbalance, it is a good test case, but its dimension according to this is actually quite small. Whereas the dim sets, yeah, even if the real dimensionality increases, this measure doesn't change much. So from that point of view, the dimensions isn't really affecting much. Okay, also we consider this kind of H-index. This is our old definition. This is based on so-called Hubner's value. And Hubner's value is defined so that we calculate the nearest neighbor. Okay, in this example I actually calculate 2 nearest neighbor, but in our calculus we still stick with the nearest neighbor definition. So we calculate for every data point its nearest neighbors, in this case these two, and then we see how many incoming pointers each data point has. So how many others thinks you as its nearest neighbors. So we can find out that this data point here is quite central because, well, it is central, and here is one incoming pointer. This also considered it as nearest neighbors, and these two. So it's central. So the question is how many these kind of hubs there are in data. In networks, social networks, and complex networks in general, this kind of hubness phenomenon is common, but how about our data? Do we have such hubness? So to estimate this hubness, what we have here is this H index is similar that has been used to estimate the impact of a journals or impact of a scholars. And it's done as follows. So first we take all of these hubness values for each of the points. We sort them in decreasing order here. So biggest first, and then smaller ones and smallest last, and then we select the rank that is smaller. So we select the rank that basically equals. So whenever the hubness value becomes smaller than the corresponding rank, then we stop, and this is the kind of the borderline. And this is what the H index will tell you. It's kind of not logarithmic, but this kind of order of magnitude decreasing order. So where this border is drawn, the further it's away, the really more hubs there are in the data. So if the hubness or this H index is small value, we have really uniformly distributed data, but if it's a big, it means that there are more this kind of hubs in the data, so it indicates that there are some hidden structure inside. And finally, distance profiles. Okay, this is basically tries to measure two different distances, local distances that are inside the clusters and global distances that are across the clusters. So these are point-to-point distances. Okay, if we know where the clusters are, we can easily calculate these two distribution and compare. But because we are doing clustering, we don't know where the clusters really are. So this might be useful measure to estimate any data that are there clusters. Is there clusters really in the data? And the hypothesis was that there should be two peaks in the histograms. And if you look carefully, there are these red ones here. You can actually find out the inside the cluster distances. They do have a tiny peak, at least with the A sets. S1, S2, it's already also there. But S3 and S4, when their overlap becomes stronger, it's just disappear and they just merge. And also merge data set, so it's pretty much impossible. And these dim and unbalanced data sets, they have clearly separated clusters, so they should be separate peaks, and yes, indeed they are. At least in the dim data sets, it's clearly separated. In unbalanced case, you can actually see that there are two different within the cluster distances. So the first distances are the dense clusters, and the second peak is for the sparse clusters. And then the distances between the clusters, they are all somewhere here. So yes, in principle you could use this kind of profiles also to estimate about your data. The G2, okay, it shows that this actually does reveal something interesting. So when the G2, when the dimension increase first, so we have a two-dimensional data sets. Okay, so I think the overlap here is 30 for the first sequence. And the dimensions increase, you can actually see that the distances, these two peaks becomes more clear. So it indicates the clusters becomes more separate, basically reducing the overlap, okay? And then if we increase the standard deviation, basically causing more and more overlap, you can also see that, yes, here we have for two-dimensional data sets clearly separated. If the clusters are clearly separated, we have two histogram peaks still here. also visible here, not so clearly, but it's still there, but then already 40, 50 and so on, it's closed. And with higher dimension of this 128 dimensional datasets, they are clearly visible. So yes, even if we go up to 60, you can still see the two peaks. Okay, now these datasets and their properties, they are summarized in this slide. So if you want to take a closer look, I recommend you to pause the video here and read more carefully. I just point out a couple of things. First, the H-index. There's not really big hardness values, except the dimensionals have some. What else? Contrast is just some number. There isn't anything clearly what we could say, except in certain G2 sets are so overlapping that the contrast becomes so small that that might indicate that they shouldn't be able to cluster it or something like that. And overlap, well, it does. It's just a measure with with the high dimensional data sets. It's really, at least the NIM sets, it's really small, and this is a quite strong indication that the clusters are very well separated. Okay, with G2 datasets, I will have a couple of this kind of slides where the overlap decreases from column when we move to the right with the columns, and then, the dimensionally increase when we move to the columns to the right, and then the standard deviation of how far, the standard deviation of the Gaussian distributions increase when we move to the down to the row. So first, if we measure the overlap with all of these data sets, you can see that if the small dimensional data sets, they have big values, they are big overlap. When the overlap increases, so even the measured overlap is also reacting to this increase of the standard deviation here. But when we move to the higher dimensional data, interesting thing is that the overlap remains 0. So according to our measure, the clusters actually become well separated when the dimensions increases. So that's what the overlap reveals. Contrast. The dimensions increase, the contrast also decreases, and when overlap increases, for small dimensional data sets there are no big changes, but higher dimensional sets we get really small contrast. And intrinsic dimensionality, well, I don't know what special could be said about this data, but there seems to be that the most significant changes when we move from increasing the dimensions happens on this area here. So then the intrinsic dimensions is increasing a lot. So starting, depending on the overlap, starting from 4 to 60 dimensions, and then after 128 or so, it still keeps increasing here, moving to the right, but not so much anymore. And almost the same behavior actually is with the hub index, H-index here. So with the dimension 16 to 128, there is a stronger increase of this value, and the dimensions increase after that. It's still increasing, but not as much. And the overlap doesn't seem to affect this index almost at all. Okay, after this quite lengthy introduction to the datasets and their properties, so let's study now how well the k-means perform. Okay, still I need some measures. So I use keep recording this kind of measure, sum of square distance. So this is the basic measure, and then normalized mean square error. This is just variation of the SSE, so that we take the kind of the mean square error by dividing by the number of data points, and we normalize it by the number of attributes. for the number of dimensions in that case? Well, the reason is simply that our old papers, if you look at those results from there are so-called mean square error used there, but it actually is measured here. So if you wonder where these numbers come from, so we have something to compare with. And then I also use this kind of epsilon to calculate the sum of squared error and the difference to the optimal solution. Well, at least if we know, or at least then if we don't know, then the best case, and the relative difference by dividing it. So this corresponds to the approximation algorithms that has been reported to have this kind of epsilon equals to 9 approximation algorithm that gives some bounds that using this algorithm the error is never higher than this epsilon value, and this kind of very theoretical results. So I just want to give the perspective where we are with the k-means and distance. Okay, so actually none of these are that interesting numbers, but the next one I will be using mostly. This is a so-called centroid index, and this calculates not just how well we optimize the closed function, but how well the cluster centroids are located. So this measure calculates, it finds out how many missing centroids there are. So it will find out these 4 clusters, they are marked with the plus here, meaning that 1 core centroid would be needed in this area. And you can see there are 2 real clusters, but only 1 centroid allocated here, all of these 4 locations. And situation, of course, is symmetric. There must be then 4 other centroids that are not needed in the area where they are, and they are marked here as minus symbols. So the centroid index will give the value for this clustering solution 4. So quite intuitive what it represents. Okay, then second measure I will use is success rate, and this is simply to evaluate because we have randomness in the algorithm. So starting with random initial centroids for the k-means, we can actually repeat the k-means many times, and then we can see sometimes how many times it succeeds and how many times it fails. And now I define the success, the case when k-means finds all clusters correctly, and how do I know it is when the ci value is 0. So here you can see 6 different data sets, all have some problems. Here we have 1 problem here we have 2 problems, 1 problem, 2 problems, and 2 problems. And this is what the numbers then express. And 1 out of 6 is a correct, perfect clustering according to this measure, and 1 out of 6 is 70%. So this success rate is what I use also. Okay, let's jump to the result. Okay, here is a summary table. So I don't tell much about this table. If you want to look at the numbers, just pause the video and study it. But I will go now selected samples from here with the examples to tell what we found out. Okay, remember we had 4 different questions to ask how k-means behaves. And the first one was the overlap. So what is the dependency on the overlap? So the S sets, well, it has the increasing overlap from S1 to S4, and now you can see, well, the numbers here is the CI values and the success rate at the above. So this is a, okay, now you can think why it's not the integer value, is because it's an average over something like 5,000 different times. So on average with S1 set, 1.8 cluster centroids are wrongly located. And interesting is that when we get more overlap, the number gets smaller and smaller. And actually the S4 dataset is the easiest for k-means. So this might be a little bit surprised, because you would think that S1 is easier. S4 is so mixed that it should be more difficult. And this is actually the case for some other algorithms. In fact, most other algorithms would find problems, more problems with S4. but for K-means it's actually the opposite. The more they are separated, the more problem it's for K-means. And the reason is just that K-means has to make local fine-tuning, and if the clusters are very far from each other, there are no freedom of movement, is changing points from clusters to each other, and no movement from the centers. Whereas when the data is well mixed, then there are more things to happen. And also the success probability here with the S1 dataset is only 3%, whereas for S4 it's already 26%. So there's a remarkably different. How much more difficult to S1 is for K-means. Okay. Second, datasets where the overlap is one parameter is a G2. And now I did this kind of trick that I did all of the 100 G2 datasets, and I just plotted according to the two variables. So first is the overlap, and this overlap is what we measure. It's not the standard deviation parameter, but it's the measured overlap of these datasets. So I put the data points according to the whatever overlap value it has, and then the second parameter is the success rate. So for each dataset, we run it 5,000 times, measure it the CI value, and see how many times it gets zero value. Okay, now I have to a little bit clarify how did we do the test, because it was not exactly like that. So let me have a little bit pause here. Okay, so how we do it with the G2 sets, because there are only two clusters. This would be too trivial for K-means or any algorithm to solve. So instead of two clusters for this test, we actually use 4 clusters. And the hypothesis is that if we optimally allocate 4 centroids here, so the real clusters are divided by like that. But now, if we have 2 clusters, 4 centroids, they should be divide the other ones. I don't know how exactly, but 2 centroids should be in this cluster and 2 centroids should be in that cluster. So that is the expected result by K-means or any successful algorithm. So instead of that, we started giving K-means exactly this kind of initialization, where we put 3 centroids somewhere randomly inside this cluster and 1 centroid inside that cluster. And then we look what K-means does it. So does with this. So the expected is that it will move 1 centroid from this cluster to here. And if it does, then we record that this is success. So that's what we are doing here. So going from 3 to 1 centroid allocation to 2 to 2 allocation, if this is a success, then we record it as a okay. So now all of the data sets, I didn't show here which data set it is. It's just kind of blind, hidden what is the identity of the data set. But the overlap and the success according to that test is now the parameters I have plotted them. And here you can see an interesting phenomenon, that when the overlap is very small, meaning that the clusters are really well separated, the success is small. It's almost 0. And somewhere at the 2% there seems to be this kind of invisible barrier, that when you cross to this barrier where the clusters becomes more overlap, so when the misclassification rate of the points increases over 2%, then the success stories start to happen. And yeah, okay, still K-means at some datasets they still have not 100%. In almost no datasets it has 100% success rate, but it has pretty much over 50% in most of the cases. There are still some borderline cases, but interesting that this kind of a jump happens around the 10%. So this overlap measure as the misclassification rate, 2% is a good indication whether K-means is able to work or not. So first answer to the first question, overlap. So how it affects K-means? So the conclusion is overlap is good. The more overlap, better K-means work. Okay, then let's study more on the results, what we can find. So how the number of clusters is the second point of interest. So let's study first with the A data set. So with 20 clusters, 35 and 50, is there any difference? And yes, there is a difference. If you look at CI values, on average, K-means get 2.5 clusters from located with the A1 data sets. When we increase the number of clusters to 35, also the error rate increased to 4.5. And the last one, 50 clusters, it's 6.6 already. But interesting, you can see also that if we compare the CI relative, and relative I mean CI divided by the number of clusters, how many percent of the clusters are wrongly allocated, is pretty much constant. So this constant, it depends on the data, how much overlap is with the clusters, how many data points and whatever the affecting parameters there are. But the number of clusters is pretty much constant. And the result is, or the conclusion is that the more clusters, the more K-means make errors. And this is pretty much linear dependency. Yeah, but in any case, 20 clusters, 35 or 50, all of these are pretty much too tough. K-means cannot solve them. The success rate is almost zero. A little bit hope with the smallest data set. Okay, another example is then the Birch2 subsets. Now remember this Birch2 subsets, we have the number of clusters reduced by taking away the clusters one by one. So now, using these subsets, I can plot the K-means results. Now, this upper curve is the represented K-means results. Later, we will see the second curve also. By repeating K-means, what we can do more. But yeah, here you can see again that the CI value, okay, when we have very few clusters, yes, K-means actually will get the zero result, so we actually will solve it. But then, the more we clusters, the more will be error and pretty much linear behavior with the number of K-means, with the number of clusters. And just to put it some perspective, here is a slide how the size of the data affects. So this was not the point of the study, but we can see K-means behavior pretty much constant, no effect on the size of the data. So the second main observation is that the number of clusters, yes, it affects the K-means performance in a way that the linear increasing with K. Okay, linear increase. Here I mean the CI value. The more clusters, the higher will be the average centroid index, or the number of clusters or number of centroids wrongly allocated. Okay, let's move on to the third question, and that's the dimensions. So okay, we have the two data sets, or two data sets is the first one. Okay, let's just see the results here, what it happens. So 32 to 1000, what is the difference? So CI values 3.6, 3.5, 3.8, 3.8, 3.9, 3.7. No change. Almost like a constant. So so K-means doesn't affect by the dimensions at all. Okay, success rate is 0%, and yeah, if we have error rate about this high, this magnitude 3 point something, so it's unlikely that K-means will find the correct solution even by repeating. And the reason is the pretty much the overlap here, but the dimension doesn't affect, so this is the observation. Second data set is this G2, and again we repeat the same test, and now look how the success rate is affected by these two parameters. First the dimensions and then the overlap. So here the overlap increases when we move down, and here the dimensions increase. And what we can see that the success for K-means is at this bottom left corner of this two parameter space. So the less dimensions and the more overlap, the better K-means does. But in the previous slide we saw that the dimension doesn't affect, so now it seems that it still affects. So dimension increase in the dimension, K-means becomes 0, success rate goes down to 0. So if we take, for example, here with the 80 80 standard deviation overlap. So yes, the more dimensions, the eventually it gets to 0. But now the reason actually is that this happens because the increase in the dimensions actually remove the overlap. So if you look at the same data sets and study what is the overlap values of these data sets, and you can see they are in this blank area, they are 0%. There's absolutely no overlap. And if you paid attention to the one of the earlier slides where there was this 2% threshold, and we have this overlap increasing to 2%, gaming started to work after that. So here you can see pretty much the same. So now we have I thought the border now between the 1% instead of 2%, but anyway, somewhere here is where you expect gaming to stop working. So yeah, increasing dimensions, you can see overlap. You just get rid of the overlap. There's no overlap anymore. So and then if you look at the gaming success rate, so this success rate actually corresponds almost directly to this overlap. So in fact, correlation coefficient is as high as 0.88. There's a strong correlation between overlap and success. Okay, when there's a correlation, one of them must be influence the other. But since overlap is a data-dependent property, so it can't know anything about k-means. So the influence must be so that if there's an overlap, then k-means success increases. So there is this kind of implication, and actually quite strong one. So it's not about the dimensions, it's about the overlap. So my conclusion from this might be a little bit surprising, but dimensionality has no direct effect on how game is perfect. Yeah. But then you have to remember that dimensions does affect the overlap, and overlap affects k-means. So in that sense, there is still dependency. So this little bit question mark can be, so no direct effect, but there is actually quite strong indirect effect. But the root cause is the overlap, or actually lack of the overlap. Okay, let's move on to the fourth question, and this is the unbalance of cluster sizes. So here we have only one data set. It is 8 clusters, 3 dense ones on the left and 5 sparse ones on the right. So what happens with k-means with using random centroids, random points as a starting solution? Well, this is what happens. Okay, if you consider random sampling, and you have here 3,000 points on the left, 500 points on the right, what is the probability to choose one point from here? Well, it is 500 divided by 6,500. I think is it something like 7%. So if you select 8 clusters, 8 random data points, I'm pretty sure 7 or even all 8 will be selected from here, because there are more to choose from. And from this 500, if you're lucky, you will select one. In some cases, you don't select any of them. Okay, so as a result, what will happen? If k-means put all the centroids in this left area here, and here is nothing. So these points, they also must select their nearest centroid. So they will usually select one of them, and in most cases they will find the same centroid which is closest. And then, well, of course, there are some points here that also map it to this centroid. Now what will happen that if we calculate this 500 points, and in this case it might be divided by the 1 cluster divided to 2, so there might be 1,000 points here. Yeah, okay, so this is already more balanced in the sense that 1,000 here and 500 here. The new centroid, it's not moving to somewhere in this area, but it's still moving somewhere. I would say it will move in 1,500, it will move 1/3 from this distance. And then you remember that distance is actually Euclidean distance squared. Okay, maybe that doesn't make my point here, but yeah. So just the end result. So So after iterating k-means, one centroid will eventually move somewhere here, typically here the center of this region, and one cluster will be find its way here. But only one, because the difference between these two areas is so the distance is so big, they are so far from each other, so no other centroids is typically moving, and therefore usually 4 cluster centroids are wrongly allocated. They are missed here, and the average CI is typically it's 3.9. Sometimes k-means happens to be lucky and select more, but in most cases it's only managed to move one. Okay, and yeah. So the conclusion of this is that unbalance is bad. If there is a serious unbalance, this kind of random starting point is not good enough for k-means. Okay, so all questions seem to be now answered. So bonus questions: can we improve k-means in some easy way? Okay, very quick, brief examples. Okay, there are, in literature you can find many papers about finding better initial solution for k-means. This is a little bit misleading because what do you mean by initial k-means? If you have some heuristics, other simple heuristic, yes, of course you can do better. But then people tend to present some more complex solutions that are basically standalone algorithms themselves. So then it's just maybe we just invent better algorithm that k-means at the first place. So okay, but anyway, so just to give some understanding how much better we can do, I consider here this random centroids, which is by default the solution that you expect to be used with k-means. So this, at least the original papers are using this. Then I allow this furthest point heuristic called this. I think this is called max-min technique. It selects the first data point somewhere in the dataset, usually the center of all data points, and then it finds out all data points which has the furthest distance to its nearest center point, and this is the only one there is. So we will find out that this data point is furthest, and then it will be selected as the second center point. And again, all data points are calculated their distance to existing, and whatever is furthest will be selected to the next one. This kind of a max-min heuristic. And two other techniques, this k-means plus and Luxburg. They are a little bit more complex variant. I would say they are reasonably good heuristic, but I wouldn't consider them as just initialization techniques themselves. But okay, let's see how well they do. Yeah, and we can do better. So CI values for, okay, this is the birth 2 subsets, but the data size is varying, so let's see how it affects. So the random was somewhere about 16 or 17 values here, and no change, no effect of the size of data. And the same is pretty much for the others. If our data size is very small, then we can get a little bit better result in some cases. So k-means plus reached the level, I think this is about 7 or 8. Max-min about the same level, slightly better. And Luxburg is from this is the most complex and also the best. It reaches about level 2 or something. So yeah, we can do better. Also with the number of clusters increasing. So this is now this is the relative CI value here. So we are expected to get, because there are linear dependency, the more clusters, the more k-means fails. So this actually is the same with these other variants also, except Luxburg is personally slightly better, so it's not affected so much on the increase of the clusters. But yeah, anyway, none of them are reaching 0%. So then second way of improving is simply repeating k-means. Okay, here I use 100 times. We could use 10 times, 1,000 times, or just run as long. If you have plenty of time, let it run overnight and let's see what comes out of there for 8 hours, 10 hours running or whatever. Yes, and it can increase the chance of success. And if we continue forever, then eventually it will solve. But because it's just a random question of random chance, when we find a good starting solution for k-means, we will test the limitations. Okay, with bird sets we can see that increased number of clusters is the k-means result, and repeated k-means. So this is the difference what we get, and also with the number of size of the data. So yeah, so this is for 100 repeats. If I repeat more, there's still improvement. Okay, the third choice is forget about k-means. Try some better algorithm. Now, a problem that you don't want to get rid of k-means because it's so simple and easy to implement. It's nice to have. So you should have something as simple as possible. So first one here, random swap, is almost as simple, a little bit more complex because there are now random swap step is added there. The repeat until loop is here, and then after the random swap, there's a local repartition which is not really needed. It could be even taken away, but for efficiency, it's included. So it makes a little bit modification of the existing centroids by trial and error manner. It's a kind of local search technique that it tests the new solution. Is it better than the previous? If yes, then it accepts, otherwise not. And it also uses k-means as an important component here. Only difference that it only iterates 2 iterations of k-means. And so basically it is same complex of k-means, a little bit added few more steps, and that's it. The second algorithm I took here is genetic algorithm, and the reason why I took it here, this is just one example of, there are many different variants what we have. I think, I don't know, is this even the complete pseudocode here, but it's already order of magnitude more complex to implement. But I choose it because it's really the best approach in general to find the best solution for clustering. So just to give some perspective. Okay, now, and these are the results for these techniques. So our lovely k-means is here. Using the random initialization techniques, what we get for all of these data sets. For some data sets it works well, some of them worse. Well, the worst data sets, because they have high number of clusters, so they are a little bit challenging for k-means. S sets, S4 especially high overlap, only 15 clusters, it's reasonably good. So on average, what we have 4.5 centroids strongly allocated, so these are the CI values. Other techniques here, the ones that I mentioned in the slide are this max-min technique, k-means plus and Luxburg. So they get, yes, they does get better. They do get better, 2.2, 2.3, and Luxburg 1.2. Repeated k-means with 100 repeats. No, I didn't test 1,000, I didn't test 1 million, so probably could still get better. 2.1. So here, this is the best of these. But then again, if we use the random swap or genetic algorithm, we get exactly 0. So the question is, the question is that if we have birds 2 data sets, for example, let's take the worst case, we have 100 clusters, out of which we have about 17 errors, so it means 17% of error rate. Yeah, well, it sounds a little bit high, but if you have birds 1, you have 6.6, so it means that about 6.6% of cases you have errors. If you are doing some pattern recognition, data mining application, you don't need to have perfect clustering. Yeah, maybe this is good enough for there, so you can use it. So that's pretty much the main question. Do you need accurate clustering or not? So if you need more accurate than the standard k-means, so you start pretty much this level, then you have to think about what to do. So repeated k-means I would have the next choice. So simple to do, no need to extra steps. All of these others you need to have some more complex implementation, especially Luxburg is already quite several steps. Even the max-min takes a little bit effort. So with the same trouble you could actually use the random swap already. Genetic algorithm really needs more efforts to do. Okay, so this is just to put the context of the game's results. So now you know when it works and when it doesn't work, and how the results compare with the other approaches. So the conclusions, so how did games perform? So with overlap, good. The more overlap, the better. So if you know that your data is overlap, you are most likely games might be good enough for you. Second, if you have lots of clusters, then it's bad. So then you should consider trying some other methods. So you are at least expecting that there are more clusters, more errors will happen. Third, dimensions. Okay, a little bit simplified conclusion here, no change. But yeah, increasing dimensions usually remove overlap. So in that case, you can also consider increasing dimensions actually might be bad. So careful with this conclusion here. And for unbalance of cluster size, yes, it's bad. Okay, that's a simplified conclusion. These are some papers I used here. If you have any questions about this, contact me.